Okay, limits at infinity of a function fx equals to the 1 over x. Okay, function fx here equals to the 1 over x, and find the value of fx. So first value of x here equals to 1. You substitute 1 here into the function. So here 1 over x, so 1 over 1 here, fx equals to 1, yeah. And the second value x here equals to fx here equal to the 1 over 2 or 0.5, and here 50, 0.02, and last here value of fx equal to the 0.001. Okay, and as you can see here, this row, the value of x, 1, 2, 50, 1000, 10,000, the value of x here moving towards to the positive infinity. So x here increase to the positive infinity. Okay, and then we check the value of y and see what happened to the y values. 1, 0.5, 0.02, and 0.001. Okay, okay, the value of y here approaching 0. So fx approaching 0. Okay, and when you write down the notation of the limits at infinity, so here write down the limits as x here approaches positive infinity. Okay, so this one, and f of fx, and then here equals to the 0. Okay, so the limits at infinity, limit as x here approaches positive infinity of fx, and here equals to the 0. So limit of 1 over x here equal to 0. Yeah, and check the graph of the rational function. So when x here goes to the positive infinity, we know that the x here greater than 0 and positive. Okay, okay, so the first value of x maybe start at the 0.001, start from here. So the value of x here increase 2, 4, 100, 1000, 10,000 to a positive infinity. Okay, and then check the value of y or the value of fx. The value of fx here approaching 0 at positive infinity. Okay, second tables, the value of x here start at the -1, -5, -100, and -1000. Yeah, function fx equals to the 1 over x. Okay, so first value -1 is substitute into the rational function, so fx here equals to the -1, and the second value -5, so here equals to the -0.2. Okay, negative 100, negative 0.01, and last year 1000, negative 0.001. Yeah. And then first you check the first row, the value of x. Okay, the value of x here approaching the very large of the negative numbers, negative 1, negative 5, negative 100, negative 10,000, negative 100,000 to the negative infinity. So the value of x here decrease to the negative infinity. Yeah. Okay, and the second row, the value of fx. Okay, so as you can see here, this row, the value of fx approaching 0, negative 1, negative 0.2, negative 0.01, and here negative 0.001. So fx, okay, so fx here approaching 0. Okay, and write down the notation, limits at negative infinity. So here x here decrease to the negative infinity, so x approaches negative infinity. Okay, and of fx, and here equals to the 0. Okay, okay, so limit of 1 over x as x here approaches negative infinity, and here equal to the 0. Yeah, and then you check the graph of the rational function. So graph of the rational function, we know that the value of x here less than 0. Okay, okay, when x here goes to the negative infinity, we note the value of x here less than 0 and negative. Okay, so maybe start from here, negative 0.01. Okay, so here the value of x here decrease to the negative infinity. Okay, and you check the value of y. So the value of fx or the value of y here approaching 0. Okay. Okay, and then find the limit of fx as x here approaches positive infinity, and find the limit of fx as x here approaches negative infinity. Okay, first method. Okay, method, you just compare the degree of the numerator to the degree of the numerator. This one is a degree of numerator to the degree of the denominator. This one is a denominator. Okay, so degree of the numerator here equals to the m, and the degree of denominator here equals to n. Yeah. Okay, first, if the degree of the numerator equals to the degree of the numerator. Here, number 1. Okay, so limit of fx here as x approaches positive infinity equals to the a over b. And then the limit of fx as x here approaches negative infinity equals to the a over b. Okay, and then examples. Okay, first examples, degree of the numerator is the same as the degree of the denominator. Okay, first here you check the degree of the numerator, this one. So degree of the numerator here equals 2, and the degree of denominator here equals 2. Yeah. So if they are equals, so the fastest way is to take the ratio of the leading coefficient. Yeah. So the leading coefficient here 2x squared over 8x squared. Okay, the highest degree of the denominator and the highest degree of the numerator. Okay, and then here limit as x approaches positive infinity of 2x squared over 8x squared, and then here you cancel, and here equals to 1, and the limit of 2 over 8 as x approaches positive infinity. So the limit at infinity here answer equals to 1, equals to 1 over 4. Okay, settle. Okay, second, number 2. Number 2, degree of numerator, denominator here. Okay, number 2, degree of the numerator m greater than degree of the denominator. Yeah, and then the limit of fx as x approaches positive infinity equals to the positive infinity. And the limit as x approaches negative infinity of fx equals to the negative infinity. Okay. Okay, then examples. Okay, so second, fx equals to the 3x squared minus 2x squared minus 2x, and over x plus 5. Yeah. Okay, first find the limits at infinity. Limit as x approaches positive infinity of fx. So here equals to the limit as x approaches positive infinity of 3x squared minus 2x over x plus 5. Yeah. First check the degree of the numerator. So degree of the numerator here equals 2, and the degree of the denominator here equals to 1. Okay, so degree of numerator greater than degree of the denominator. Yeah, so your limit will be equals to the positive infinity or equals to the negative infinity, depend on the leading coefficient. Yeah. Okay, so you compare the leading coefficient. So here, okay, so write down the limit as x here approaches positive infinity of 3x squared over x. Yeah, and then here equals to the limit as x here approaches positive infinity, and here you cancel, so equals to the 3x. Okay, so find the limit of 3x, x here approaches positive infinity, and then you substitute infinity here into the function, and answer here equals to the positive infinity. Okay, so limit of fx, x here approaches positive infinity, equals to the positive infinity. Okay, and then second, find the limits at infinity. Okay, so here find you compare the leading coefficient, the highest power degree of the denominator. Okay, okay, so the highest power, the highest degree of the numerator here equals to the 3x squared, and then here equals to the x. Yeah, so find the limit as x approaches negative infinity of 3x squared over x, and then here you cancel, equals to the limit of 3x as x approaches negative infinity, and then you substitute negative infinity here into the function. So answer here equals to the negative infinity. Yeah. So the limit of fx as x approaches negative infinity equals to the negative infinity. Okay, and number 3. Okay, number 3, degree of the numerator less than degree of the degree of numerator less than degree of the denominator. Yeah, and find the limit of fx as x approaches positive infinity, and here equal to the 0. And second, limit of fx as x approaches negative infinity, and answer here equals to the 0. Yeah. Okay, find the limit of fx as x approaches positive infinity equals to the limit of x squared plus x plus 1 over x cubed plus 5, okay, as x approaches positive infinity. Okay, first here you check the highest power of the numerator. So the highest power of the numerator here equals 2, and the highest degree of the denominator here equals 3. Okay, so power here 2 and 3, so you compare, and then write down the limits. Okay, as x here approaches positive infinity. So the leading coefficient of the numerator x squared, and the leading coefficient of the denominator here equals to the x cubed. Okay, so here write down the limit as x here approaches positive infinity. So here you cancel 1 over x. Okay, and then substitute infinity here into the function 1 over infinity, and then limits of fx, or limit of the x squared plus x plus 1 over x cubed plus 5 as x here approaches positive infinity equal to the 0. Yeah.